This question comes from Leo, who asks, what if we built an elevator to space? You might imagine a sleek, futuristic elevator car gliding silently up a thin ribbon, connecting a tropical earthly port to a bustling station among the stars. It makes a certain kind of sense. We build tall structures, we ride elevators every day. How much harder could it be to just keep going? The truth is, a space elevator is not just a very tall building. If you tried to build a tower that high out of steel, it would collapse under its own weight long before it reached orbit. The forces of gravity and physics are, to put it mildly, not on our side. So, the classic design doesn't rely on compression like a tower. It relies on tension, like a rope. The idea is to have a single cable, a tether, anchored to a platform on the equator and extending up into space for a staggering 35,800 kilometers. But here's the twist. The real anchor isn't on Earth. It's in the sky. At that specific altitude, a point called geostationary orbit, an object orbits Earth at the exact same speed the planet rotates. From the ground, it would appear to hang motionless in the sky. So, you attach your cable to a satellite at that point. But to keep the cable taut, you have to extend it much farther out, another 50 or 60,000 kilometers, and attach a massive counterweight, perhaps a captured asteroid. Now, the centrifugal force pulling the counterweight outward balances the gravitational force pulling the cable downward. In theory, it's perfectly stable, a bridge to the stars. The problem, the single biggest problem, is the cable itself. The forces involved are beyond astronomical. The tension would be measured in tens of gigapascals. The strongest steel we have would snap under about 1/100th of that pressure. Trying to build a space elevator out of any known metal would be like trying to support the weight of a mountain with a piece of wet spaghetti. For decades, this is why the space elevator was a permanent resident of science fiction. Then we discovered a material that might just be strong enough: carbon nanotubes. These tiny cylinders of carbon atoms have a theoretical tensile strength that is literally off the charts. They are the only material we know of that could possibly withstand the unimaginable strain. But, and there is always a but, we have never made a carbon nanotube longer than a few feet. We need to make them tens of thousands of kilometers long perfectly, without a single atomic defect. One tiny flaw, one weak spot in that entire unimaginable length, and the entire structure fails. And you absolutely do not want to be on Earth when a 35,000 kilometer long cable under immense tension suddenly fails. So, what happens if it breaks? The answer is terrifying, and it depends entirely on where the snap occurs. If the break happens near the anchor point on Earth, the entire system, now feeling the full outward pull of the massive counterweight, would whip away from our planet. It would slingshot out into the solar system, 100,000 kilometers of ultra-strong ribbon flying off into the void like a cosmic-sized bolus. But if the break happens high up, above the geostationary point, that's the true nightmare scenario. In this case, the entire length of the cable would now be orbiting faster than the rotational speed of the Earth below it. It wouldn't just fall, it would wrap itself around the entire planet. Not just once, multiple times. A razor-sharp ribbon of carbon nanotubes, thousands of kilometers long, would cinch around the equator at hypersonic speeds. It would be the single largest kinetic energy event in human history, effectively sanding the surface of the planet clean along the entire equator. The energy release would make every volcanic eruption and asteroid impact in history look trivial by comparison. So, the diagnosis? A space elevator is perhaps the most beautiful and terrifying infrastructure project ever conceived. It's a delicate dance between impossible material, science, and planetary-scale catastrophe. But if we could ever build it, it would revolutionize our future, turning the cost of reaching orbit from a fortune into the price of an electricity bill. The question is, are we willing to gamble the entire equator on a thread that's one atom thick?